Okay, hey everybody, welcome back. Good morning. Hope you guys are doing well. Getting a good early start today. It's Friday. It's April 10th. This is Chapman, our 10 a.m. to 10:50 group, and welcome back, everyone. Good morning. I know it's a little earlier than 10 just now. I'm just getting things started so that you can have some time to arrive. But anyways, welcome. Be getting our lecture going right at 10, so we've got a few minutes to spare. But just get yourself comfortable, and hopefully your viewing setup is all good. Good morning. Okay. Good morning. Hey, Jackson. Good to see you. Hey, Kitty. What's up, everybody? Wonder what you guys are doing. Video games over there? Anything? I'd love to have some recommendations. Kitty. Netflix shows. I'm all ears, so if you have anything, throw it out there. She's such an attention hog, huh? She just wants to be on camera. Kitty, I didn't know this about you. Can we get a YouTube channel going for just Kitty? What's up, Kitty? Huh? What's up? Welcome. This girl is crazy. She's always getting into some. Good morning. Her name's Kitty, straight up, Kitty. Good kitty. Yeah. She's been a little thrown by all these lectures. I don't know. She's like, what are you doing? Why are you always talking? But yeah. Come on, Kitty, you'll get used to it. She's really happy. She's purring. Good kitty. 16 years old. I'm very proud of that. It's going strong. Since 2004. Still a few minutes, so we're just hanging out, waiting until 10. Kitty enjoying a little bit of downtime, huh? Anybody got pets? I wonder. I wonder if anybody got a pet older than mine. Older than 16, anybody? Good kitty. What's up? Good morning. Hey there. Kitty. What's up? Yeah, 16. Still going strong. I mean, is she like older than you? You guys are like 18, 19, right? So, good morning. Good morning, everybody. Hope you got a nice start, got your coffee going, whatever it is. Ready to kick back and help us out, get through this notes on Einstein. That's the mission today, talk about Albert Einstein. So just about another minute until it's 10, and then I'll go right into it. She always does this. She'll be like, if I'm grading or reading something, she just tries to block me. She tries to like literally get right on top of my notes. These are my notes. I mean, so yeah. Kitty, don't you get enough attention already, huh? Anyway, cool. Oh, good girl. Good kitty. Yeah, so almost ready. Got a little guest. All right, guys, so it's pretty much that time. I'm going to go on then and get us started and let Kitty just hang out on the notes for a little while. So welcome back, everybody. Good morning. It's Friday the 10th. This is 10 a.m. meeting for Philosophy 101. And today we're having an important transitional kind of meeting because we're going on to another topic. Last lecture, we kind of wrapped up everything that we had to when it came to the work of Descartes and the epistemology subject. So epistemology was the last topic. That's all about knowledge. We've covered 3 big topics so far in the semester. We started with philosophy of religion, and then it was ethics, and now we finished with epistemology. I guess just when it concerns epistemology, there was the ancient definition of knowledge, justified true belief. Then there was Gettier's criticism of that, showing that you could have justified true beliefs and still not have knowledge. And then after that, Descartes, who said, let's find out what is certain. And if we can find out what's certain, then we can use that as a basis for all the scientific knowledge that we're rapidly developing. He thought that you'd use the method of doubt to discover what's certain. And the method of doubt says to assume that something's false if there's any possible way to doubt it. But one thing he says that you can't doubt is that you exist because you're thinking. So I think, therefore I am. It's not possible to doubt your existence. It's kind of self-contradictory to try and doubt one's existence because even the thought, do I exist, has to be given by some being that has the ability to think. And therefore, even if everything you're perceiving is in a dream, there's still this dreamer that you are, and you have first-person access to your thoughts. So your thoughts verify that you do exist, even if everything else is false. After that, he says that the knowledge that we have, even of physical objects, is more rooted in our intellect and mind than our physical 5 perceptions or senses. So he gave the example of wax. Wax at a certain moment in time might be blue, smell like flowers, taste like honey, hard, cold, but if it's heated by a flame, then it loses all those qualities, but nonetheless, it still exists. And the thing that's remains in place over those changes is that it's still extended, flexible, and changeable. Those qualities are things that only the mind can apprehend because they are the recognition of how it endures across changes. So he thinks then that the 5 senses tell us only non-essential facts about the nature of objects, and certainly about ourselves, because we more directly intuit that we are thinking things than embodied beings, since the existence of the body is subject to doubts that the existence of the mind is not. So anyway, that was Descartes, and now we move on, and we have another important subject that we're going to go over for a couple of meetings, and this is the topic of metaphysics. So another big branch of philosophy is what they call metaphysics. And in its original meaning, it meant it's coined by the philosopher Aristotle, ancient Greek philosopher, introduced this term. It would literally mean to go beyond the physical, but it's kind of acquired a more precise meaning over the years. It's basically a deep investigation into the nature of reality and what exists. So one inquires into what exists. So the questions include what exists and what is the nature of the things that exist. So that's metaphysics. It's broadly described as a focused, deep inquiry, investigation, exploration into the nature of reality. And when we ask the questions about what reality is, what's really real behind the appearances that we think we're seeing, what's the real fundamental deep nature of objective reality? The questions then expand into, well, what exists in this reality? And what is the underlying nature or characteristic of the things that do exist? So within metaphysics, there's many different topics that metaphysicians can pursue. One subject could be the question of free will. Does free will exist, or are we just determined to act as we do? So do human beings have free will? Are we in control of our behavior, or are we just sort of cogs in a larger physical system? Another question could be, how do things persist over time? Like, what are the criteria for a thing to remain self-identical over time? For example, you exist, and you also existed 10 years ago, but all the physical cells in your body have been replaced from that time 10 years ago. So you don't have any physical continuity to the object that you were 10 years ago, and yet you still exist. So questions could be asked, what does it take for an object or a person to maintain identity across change and across time? We could also ask other questions in metaphysics. What's the nature of objects, properties, and so forth? But the question of metaphysics that I've chosen for us to talk about and to read about is the metaphysics of time. So we are now going to explore and investigate that part of reality. What is time, and what is the nature of time? So that's the subject for us, time. Now, when it comes to time, it's something that we're all very familiar with. All of us are living lives according to time, and we're all familiar with the way that it organizes our behavior and our actions. You keep a schedule, you know the time at which you're appointed to do things. Like, for example, you know that this class meeting starts at 10 a.m. on Monday, Wednesday, Friday. You know how much time has passed within a given interval, or how much time remains for a certain event to conclude. You know how long you've been alive. You know the age of your parents, or how long it takes to, let's say, complete a semester or a college education. You know how much time remains in all these things. So we organize our lives according to the clock, and we live and die according to the passage of time. But the thing is, even though we're so experienced in a way dealing with the concept of time and moving in the world according to our time and our schedules, when you ask deep questions like, what is time though? What is it actually in its deeper analysis? You find that it's quite puzzling and mysterious, not so easy to describe as the common sense everyday experience of it might seem. So that's what we're going to try and do. We're going to try and get a deeper handle, a deeper understanding of what time really is and what the most current theories say about it, that go beneath the everyday layperson's experience of it. So yes, time. And the first author that we're going to study on time is Albert Einstein. So today's lecture is about the writing of Albert Einstein. So Albert Einstein lived from 1879 until 1955. That's Einstein's lifespan right there. In 1906, he was a pretty young man, and he was working in a patent office in Germany. And basically, he thought, well, I've got some free time when I'm not just clearing patents and evaluating patent applications. And he had like a degree already in physics. So he's really smart and an excellent student. And during his free time at the patent office, he would read all the most cutting edge papers in physics. And he was working on he was working on some of his own theories and ideas. That's where he wrote and published in 1906 the general theory of relativity. The paper, I believe, is called On the Electrodynamics of Moving Bodies. And those papers, the general and special theory of relativity from 1906, they were considered so important and revolutionary that they won the Nobel Prize in physics. And then he was only a young man too. I mean, think about that. 1906, basically he's around 26 years old or whatever. And at that young age, he's writing papers from an office space that fundamentally revolutionized the understanding that we have of space and time and our position in the universe relative to space and time. So completely overturned the Newtonian paradigm that existed before him, and at such a young age. So I mean, anyway, we all know, we've heard Einstein is very smart, but it's totally impressive the way that he was able to craft these theories from the security of an armchair, unlocking deep fundamental secrets of reality. So 1906 is when he published those initial papers. The thing about them is they're very technical, and they're not so easy for the average Joe to understand without formal training in physics and math. But in 1916, he wrote a book that's 10 years later. This book was trying to bring it to a wider audience, to make it a little bit more easy for the average person to comprehend. So from 1916, Einstein's book is called Relativity. So in that book, he kind of tries to bring down to earth a little bit some of these heady ideas so that more people could comprehend them. It was written in a less technical format. And anyway, the selection that we're trying to read today comes from that book. Our textbook has taken one snippet out of it, and as you've seen in a few other cases, has retitled it. Like for example, Pascal's wager came from his book Pensees, but in the book they just retitled it The Wager. So in this case, our text has taken a section out of the 1916 book Relativity, and they've gone with this title: Time and the Relativity of Simultaneity. Time and the Relativity of Simultaneity from Einstein from 1916. Okay, so that's our topic today. That's the writing that we want to go over. Okay. So Einstein, as I was saying, he's famous for revolutionizing our common understanding of space and time. A lot of people, I'm sure, have heard of Einstein. It's a household name, pretty much. I would say that in the West, he's probably almost the iconic stereotype of the genius scientist, right? He almost is like the visual stereotype with the big puffy white hair and the tweed coat and everything else. So he's attained this kind of iconic status in our pop culture even, but people don't all know much about his ideas, even if they've heard his name. So what we're going to try and do is at least get a gloss, a sort of handle on the basics of the theory of relativity when it concerns time. So I'm taking us on a crash course through some of the ideas here. He revolutionized our understanding of time and space because of the following reason. Prior to Einstein, we were operating within views of Isaac Newton as the dominant conception of space and time. In Newton's paradigm, time and space were independent of each other. So Isaac Newton thought that no matter how fast, no matter how slow objects move through space, no matter what their velocity may be, that could have no effect at all on the passage of time or the rate of time's passage. So that's what Newton believed. Time and space were not related to each other. Space is just where things move around and have their different velocities, and time is this constantly passing structure that has no relationship to how fast or slow things move in space. What Einstein showed was that this is not correct, that time and space are not independent of another, but in fact they're integrated into one unified structure, which is called space-time. And according to this space-time theory, which is highly well confirmed by empirical studies and evidence, the velocity that objects are moving through space can affect the passage of time relative to other observers that are moving at different velocities or are in a state of rest. So basically he showed that how fast or slow things move relative to other objects in space can affect the relative time that has passed for that observer that has that state of velocity. And this, when you understand the integration of space and time according to this theory, you're going to see that it's extremely deep, very puzzling and weird, and it has far-reaching and puzzling implications for our understanding of ourselves and our place in the universe. So let's try now break it down, get into the real details of this author's work. So he begins with this. I'll just erase this stuff because we've now got it. He starts off with a scenario that he would like the reader to think about. He says, imagine if you can that there's a railway embankment, basically a railroad track. That's what this, let's say, horizontal line stands for. And then suppose that lightning strikes the railway at 2 points, A and B. So here's A, labeled as A, and here's B. Now suppose that there are 2 lightning strikes that occur on the railway track at points A and B. 2 lightning strikes happening on that track. Next thing is this. Assume that those 2 lightning strikes happen simultaneously, right? Suppose they happen simultaneously. Einstein has a question for you, the reader, that's it's like a deceptively simple question. It seems really simple and straightforward, but it's actually not so easy to answer. The question is this. We said that the 2 lightning strikes happen simultaneously. Question, what does that mean? What does it mean for 2 events to happen simultaneously? The reason that this is a kind of hard question to answer is because try to answer it. If you do try to give any stated definition of simultaneous, your most natural instinct will be to say something that just says the same thing over again. Like you might say simultaneous means happening at the same time. But same time as is just circular for the concept of simultaneous. We're asking the more fundamental question, what does it mean for 2 events to happen at the same time? Can anybody say? And I'm sure that if I ask you right now, tell me what you think simultaneous means. You'll find it very hard to say something that does not just boil down to they happened at the same time. Because can anybody try? I mean, it's not very easy to do, but if you have a way of trying to put the concept on the table, tell me what you would tell somebody simultaneous means. I mean, if you find it like a struggle to write anything down that doesn't just say happening at the same time, then you're in good company. Good, William. Yeah, because Einstein, the great genius himself, knows that it's not so easy to define this concept as it seems at first. It seems like a trivial matter, some word that we use all the time, or that when someone uses it, we understand them immediately. But if a person asks you, give me a more precise account, what do you mean, same time? You'll just kind of shrug and be like, I don't know, same time. You know, keep repeating yourself, going in a circle. So he says this won't do. Let me read to you then his questions and his opening statements here. He says, lightning has struck the rails on our railway embankment at 2 places A and B, distant from each other. I make the additional assertion that these 2 lightning flashes occurred simultaneously. If I ask you whether there is meaning to this statement, you will answer my question, yes. But if I now approach you with the request to explain to me the meaning of the statement more precisely, you find after some consideration that the answer to this question is not so easy as it appears at first sight. Okay, the next thing that he says in the next paragraph is that in light of his question, what does simultaneous mean? Some people might say, well, it's actually kind of difficult to say, but who cares? Because we don't really need to have a definite definition of it. We just have a word, and when people use it, we basically can follow what they're saying. So does it really matter if we have like a very clear definition? Can't we just have our words simultaneous and say, kind of waving our hands, it means something. It means something like same time. And come on, Einstein, leave me alone. Why do I have to be more detailed than that? Einstein says, no, this is not good enough. We cannot use a word with an undefined concept, at least not in science. He says, for a physicist, and really even for an everyday person, If you use a word, but you don't have any understanding of what it really means, and you can't explain it, then maybe that word does not actually have a meaning, and you're just fooling yourself when you think that it has a clear understanding. So he says this is what we need. We need a clear enough definition of simultaneous such that we could use that definition to conduct an experiment to determine whether the two events seen here are simultaneous or not. So then that's the way Einstein frames it. He says, I would like us to come up with a test that could be used to verify whether or not the two events seen here are simultaneous. So what could be a physical test for simultaneity? And he says if we don't have the means by which to construct such a test, then we might be using a word that actually doesn't have any meaning at all. So let me read then what he said, and you can hear his own statement of it. After some time, perhaps, the following answer would occur to you. Now he's saying this is what someone might say back. The significance of the statement is clear by itself and needs no further explanation. Of course, it would require some consideration if I were to be commissioned to determine by observation whether in the actual case the two events took place simultaneously or not. Einstein responds, I cannot be satisfied with this answer for the following reason. Suppose that as a result of ingenious considerations, a meteorologist discovered that the lightning must always strike the places A and B simultaneously. Then we should be faced with the task of testing whether or not this theoretical result is in accordance with reality. We encounter the same difficulty with all physical statements in which the conception simultaneous plays a part. The concept does not exist for the physicist until he has the possibility of discovering whether or not it is fulfilled in an actual case. We thus require a definition of simultaneity such that this definition supplies us with the method by means of which, in the present case, he can decide by experiment whether or not both the lightning strikes occurred simultaneously. So we need some way to establish an experiment that will confirm whether they were simultaneous or not. And then he says, as long as this is not satisfied, I allow myself to be deceived as a physicist. And of course, the same applies if I'm not a physicist, when I imagine that I'm able to attach a meaning to the statement of simultaneity. And then he says, I will ask the reader, do not proceed further until you are fully convinced on this point. So he says there, basically, breakdown of what has gone so far. Suppose there's these two lightning strikes on the railroad. Say they happen simultaneously. Question, what does it mean that they happen simultaneously? Not so easy to say without just repeating the concept in similar words. Someone might argue, who cares? It's not something that we need to have a more definite understanding of. Einstein says, no, it has to be very clear. It has to be so clearly defined that we could test whether or not the two events are simultaneous. And if we don't have the ability to make such a test, then we might be operating with an undefined concept that is actually meaningless. So next up, Einstein is going to tell us what experimental test could be performed, could be conducted to establish whether those are simultaneous lightning strikes. So he gives us the idea next of that type of test. So what is the test by which we can determine whether those are simultaneous events? Here's the idea he gives. He says, all right, consider the length from A to B. That could be thought of as like a line segment, the line segment AB. Now, is there a midpoint intermediate between A and B? And just a quick refresher from our studies in geometry, if you guys ever have, or if you're currently studying that subject, it's also just common sense. Can we agree there's definitely a midpoint that bisects the line segment AB? So let's say this is the midpoint M. Now, let's place an observer there, standing motionless at M. This is the observer at the midpoint. Midpoint observer positioned at M. So, is this observer the same distance from A as he is from B? Yes, good. He is the same distance between the two events. That's why it is a midpoint by definition. Okay, now, next thing is this. Place this observer at the midpoint and make sure that he is far back enough from A and B that he can observe the two regions of space in one field of vision. Basically, what I'm saying here is he has to be able to see both A and B without turning his head or casting his gaze from left to right. Why is that important? I hope it's somewhat clear, but I want to make it exactly clear. If he was, let's say, too close to the A, and he could not see B at the same time, so like he looks at A, and then he sees lightning strike, and he quickly looks over towards B, there he sees lightning strike there. Under those circumstances, he could not actually conduct this test, right? Because the interval of time in between when he looks at the one event and the other could have been the time lag in between which the first event started happening and then the second one did. So obviously you cannot assess whether they're simultaneous or not unless you could observe the 2 points A, B in one common field of vision. So let's understand that. That means we have to position him at a midpoint that's far back enough so that he can just look at A and B in one field of vision, in one visual perception. If he's not far back enough, then let us outfit him with some type of mirrored device which can refract the light cast from one of the positions so that he can look at that and use that as his substitute for being far back enough. Anyway, we have an observer at M, and basically we just want him to be able to see the whole scene at once. Now, how does vision work? How is it that you're, for example, able to see the computer screen or whatever device you're looking at right now? How does it work? It works by means of the light rays that are bounced off of and reflected from the surface of the object, then traveling towards your eye and being collected in your retina and then processed for the visual information by the brain. So you may understand then that since it takes light to see things, when you're looking at objects, you can only see them because of the transmission of the light rays from the objects to your eyes. Why is it that when you close your eyes, you cannot see anything? This is, I hope, an obvious, clear fact. It is because when your eyes are closed, the eyelids block the incoming light from reaching the surface of the eye, and therefore you cannot see images that come to you through the light rays. So light is needed to transmit visual information to a perceiver. Now, the distance from A to M is the same distance as from B to M. They're equidistant to the observer, in other words. So let us say that this observer at M witnesses the two lightning strikes happening at once from his midpoint position. That would establish that the two events occurred simultaneous relative to him, but only if we make one further stipulation, and Einstein talks about this. We have to assume that the speed of light is always constant and it's always fixed. Essentially, we have to assume that the speed that the light moving from A to M is the same velocity as the light moving from B to M. It's only on the basis of that assumption of the common universal speed of light that never changes that this test situation could verify that the two events were simultaneous. Because given that the light has traveled from A to M the same distance that the light has traveled from B to M, and given that they are received by the observer in the same perception, that means they've traveled a common distance, and if the speed is the same, then having arrived at a common endpoint over the same distance traveling at the same speed, we can infer that they departed from their origin points at the same time, right? But if the speed of light was different from A to M than it is from B to M, then this inference could not be made. For example, let me give you an analogy here. Suppose that the situation is this: A and B are two runners at the starting line of a race, and this is the finish line, M. Suppose that A and B, the two runners, coincide and cross the finish line at exactly the same time. But I'm going to add one more fact to this example. Suppose that runner A is twice as fast a runner as runner B, okay? He moves twice as fast than him. But they've reached the finish line at the same time, and they've gone the same distance. So with those facts in place, tell me which one of those two runners left the starting line first. If A is twice as fast and he meets B at the finish line at the same time, then which of them would have departed first if that's the situation? Let's see you give me the answer. The explanation given, or the example given, is A and B are runners running to the finish line M. They both reach the finish line at the same time, but A is twice the faster runner. Good. That means that B left first, and was given a head start. Halfway through his run, A starts running, and because he's twice as fast, like the tortoise and the hare example for the sake of discussion, he catches up and reaches the finish line at the exact same time. But hold on. We want to say that light doesn't operate like these two runners, moving at different speeds. And so if we assume that light always moves at the same speed, then we could deduce that they departed from A and B at the same time. Not like, for example, the light moving from A is twice as fast, so it let B have a head start, and it just chose to start departing from A halfway later, okay? So if the speed of light is constant and fixed, moving from the same velocity from A to M as B to M, if they reach M at the common terminal endpoint, which the person perceives at once, then given the fact they've traveled an equal distance and have reached the same destination, that means they have departed their origins at the same time, and in other words, are simultaneous. I'll read to you then his discussion of that. He says this: after thinking the matter over for some time, you then offer the following suggestion with which to test simultaneity. By measuring along the rails, the connecting line AB should be measured up and an observer placed at the midpoint M of the distance AB. This observer should be supplied with an arrangement which allows him to visually observe both places AB at the same time. If the observer perceives the two flashes of lightning at the same time, then they are simultaneous under these conditions. And then there's this part about the speed of light. He says, I'm very pleased with this, but I cannot feel the matter totally settled because I must raise the following objection. The definition would certainly be right if only I know that the light by means of which the observer at M perceives the lightning flashes travels along the length A to M with the same velocity as along the length B to M. And then he continues later by saying that light requires the same time to traverse the path A to M as for the path B to M is a stipulation which I make of my own free will to arrive at the needed definition of simultaneity. So this then becomes the precise measure of simultaneous events and how to define the concept. We say events happen simultaneously if an observer positioned equidistant between the events observes the two things happening in one common field of vision. Now, using this idea of simultaneity, an observer witnessing the light emitted from the two events reaching his visual system at the same time, we then use that concept to define the simultaneity of any two events. So take, for example, the use of clocks. Clocks are just a way of coordinating our behavior in space and time. If we all have synchronized watches, which have pointer hands, for example, that move at a common fixed rate, then we can use that to say, for example, you should be doing these things or observing these events when the pointer hand of the clock indicates a certain time. So, for example, this class meeting starts at 10 a.m. You could think about it this way. What two events should be happening simultaneously for you to be at this class at the correct time? It would be that the pointer hands of your measuring instrument or clock indicate 10, and you observe that indication at the same time as you are witnessing, let's say, the live stream beginning. That's how we organize and say of two events that they're simultaneous. But it gets a lot weirder just next. So there's the really trippy, strange part is what develops next, because what we're going to learn now is that this definition of simultaneity indicates that there's no such thing as objective simultaneity, that it's actually relative. And that is quite deep and puzzling, and we're going to get into it now. So, new question. Are the same two events which are simultaneous with reference to this observer simultaneous relative to other observers? And we're going to show that that is not true, that simultaneity is not absolute or objective. So next up, we're going to add a second observer to the situation. This guy is still here, but now there's another person who's on a train, and the train is moving along the tracks from left to right with a constant velocity v. In this other frame of reference, there's an observer on the moving train. Okay, so this is a guy on a train traveling the railway, going away from the direction of A toward the direction of B in a constant state of motion from left to right. Now, the observer who's on the train, relative to him, the train is his frame of reference because that's the body whose state of motion he possesses. And therefore, there's a frame of reference defined by any observer who has a different state of motion than another. So one frame of reference is the motionless observer's vantage point standing at M. Another frame of reference is the events as they are seen by observers who possess the velocity of the train traveling with it. So now, as he passes by these events, let us say that he also traverses the midpoint of A and B as it is seen on the moving train. Let us call it M prime. Okay, so what is M prime? It's the midpoint of AB, but as seen by the observer who's traveling with velocity v along the railway. Now, I want you to imagine this, that while he is moving along this pathway, at the exact moment that he is traversing the midpoint, let us assume that he's perfectly aligned with this guy. So there's like a plane described by the midpoint, and at one moment, a split second in time, they're both aligned on that plane, okay? Now suppose that when he crosses M, the motionless observer does his observation of the strikes of lightning, seeing them from his perspective as simultaneous events. This guy, though, is passing through that midpoint with constant velocity v, so he does not remain permanently at M prime. He's there for a brief split second, but he's carried to the right with the velocity of this train. While he passes M prime, he intersects with this person's observation point. At the same point in time, he conducts his observation. Now, question to you. Based on what we've said concerning the way that vision and the transmission of light rays to the eye works, do you think that the second observer will also see the two events happening simultaneously like the first observer did? Will he see the two events as simultaneous or not, the guy on the train? And again, I'm asking you to consider it from the point of view that he passes through M prime. If I could give you one more example, if this was like a playthrough of a video, then if we hit pause at the exact moment that he passes M prime, like pause, it's in motion, pause, he's right there at M prime, we would see that in that freeze frame, he's lined up with this guy and he's conducting his observation. But when we hit unpause, he's not going to stay at M prime, he's going to stay at M. And he's going to continue traveling to the right with velocity v. So Brian, you say something which is correct. You say that the moving observer, the observer on the train, will not see the two events happening as though they are simultaneous. And that's correct. So here's the next question for any of you. Which one will the moving observer see happening first, according to his condition of observation and his state of motion? He won't see them happening simultaneously like the other guy who's standing still. No, it's not A. It's not A. So, I mean, it's B. But let me help you understand why it's definitely not A. When he passes through M prime, which one is he getting closer to? He's getting closer to B. He's rushing towards B, and he's going away from A. So the light rays that have to reach his eyes in order for him to perceive anything cannot reach him at the same time because he's asymmetrical between the distance of A and B, unlike the other person. You see, he's rushing out farther from A, closer to B. So the distance between his body and his eyes and the emission of the light source, right, when it concerns B, is a shorter distance than the interval of space opening up between himself and A as he runs away from it. So since the speed of light is constant and doesn't change, the same light ray moving at the same velocity can't possibly reach him at the same time because he's a moving target. He's getting further from A, closer to B. So the light ray coming from B has a shorter distance to travel to reach him. So it will reach his eyes first, and A will catch up to him a moment later. So given this second observer's state of motion, A is seen as happening second, B is first, and A is second, because of the asymmetrical distances involved. Let me read to you about it, and here's what he says. So up to now, our considerations have been referred to a particular body of reference, which we've called the railway embankment. Now, Let us suppose a very long train traveling along the rails with the constant velocity v in this direction, indicated in figure 1 on page 456. People traveling in this train will use the train as a reference body, and they will regard all events in reference to the train. So the question arises, are two events, the two lightning strikes, which are simultaneous with respect to the embankment, also simultaneous relative to the train? And we shall show that the answer must be no. Now, when we say that the lightning strikes A and B are simultaneous with respect to the embankment, we mean the rays of light emitted at A and B, where the lightning occurs, meet each other at the midpoint M of the length A to B of the embankment. But the events A and B also correspond to these two positions as seen from the train. Let M prime be the midpoint of the distance A to B on the traveling train. Now, just when the flashes of lightning occur, this point coincides with the point M. But it moves to the right in the diagram with the velocity v of the train. If an observer sitting in position M prime in the train did not possess velocity, then he would remain permanently at M, and the light rays emitted by the flashes of lightning A and B would reach him simultaneously. But in reality, he is hastening towards the beam of light coming from B, whilst he is riding on ahead of the beam of light coming from A. Hence, the observer will see the beam of light coming from B earlier than he will see that emitted from A. Observers who take the railway train as their reference body must therefore conclude that B takes place earlier than A. And we therefore arrive at the important result. Events which are simultaneous with reference to the embankment are not simultaneous with reference to the train, and vice versa. Every reference body has its own particular time, and unless we are told the reference body to which the statement of time refers, there is no meaning in the statement of the time of an event. Okay, so I mean, that is the really deep, fundamental insight that Einstein discovers here, that the same two events, A and B lightning strikes, are either simultaneous relative to one condition of observation and one state of motion, and then they are non-simultaneous relative to another condition of observation and a differential state of motion. Now, it's very deep and weird, because here's the thing. You would have thought that there's no way to reorder the sequence of events in time. You might have thought that there's an objective ordering to the way things play out, so that if two events are simultaneous, it's not also true that one happens before the other. But now that seems to be the case. Let me make sure that we're all tracking this. What's the answer to my question? Are the two lightning strikes simultaneous or not? And I'll just give you a hint that it's kind of a trick question. But what would you say based on what I've now taught you? Are these two lightning strike events simultaneous events, or are they not simultaneous events? Correct. It is relative is the right answer. I'm glad that you gave that answer and not the answer that they're really simultaneous, because sometimes students misunderstand that. Sometimes a person might think, well, you know, this guy is seeing it as it actually is because he's standing still. This guy sees like some illusion of the actual case because he's moving, but that's not right. Neither one of these two observers can claim a privileged position from which they're observing such that that is the correct one. What does it mean that they're relative, Brian? It means that there's no answer to the question, are they simultaneous or not? It depends on the state of the observer and the velocity of the objects moving relative to that observer in their frame of reference. So what it means is that you cannot say with an objective answer that they are or are not simultaneous. In the nature of reality, there's no factual answer to that. In one observer's experience, they are, and in another observer's experience, they're not. But neither one of them is the so-called right observer that gets it correct. It's just relative. Now, you might have thought he's really getting it right and the other guy's not because he's moving. But I was just going to say that's not the way to look at it, because no single observer has a privileged point from which to observe. In fact, even when you think you're motionless, everything is in a state of motion. Even, for example, you right now sitting still perhaps are moving with the frame of reference of the planet Earth, which is constantly orbiting the sun. So none of us can say that we observe things from some type of uniquely objective point of view. And therefore, no observer can claim with objective clarity that their condition of observation is the so-called right one. Caesar question: what if you had two sensors that can measure the exact time that two lightning strikes the track? Wouldn't that be objective? No, the sensors would also disagree. If you had two measuring instruments, they would collect light from the two events at different times. If one measuring instrument was motionless, it would receive the two light sources simultaneously under these conditions. And if another one was placed on the moving train, it's going to receive the light source from B before A. So no, Caesar, it's not the case that this is just some kind of quirk that results from the way we're defining concepts or from the way we're measuring things. It's deep in the nature of reality that these are relative and that there's no objective fact about how they occur, in what order. And let me make it even more weird. Suppose we had a third observer that's traveling in the opposite direction on a separate stretch of the track, moving from the direction of B toward the direction of A. If this third observer passed through, let's say, midpoint M double prime, and they intersected with the midpoint at the exact same time as the other observers were aligned along that parallel plane, tell me, what would the third observer see, given that they're moving from right to left? They would see which event happening first. And it's for the same reason, just in the opposite direction. You can tell me what? A would be seen first, correct. Because in that case, the distance between the observer and A becomes shorter than the distance between the observer and B. And the asymmetric lengths that the light sources have to travel moving the same velocity would reach this moving target of the observer's perceptual system at different time points. So we've got this very puzzling set of facts now. Concerning these two lightning strikes, A and B, we've been told that there's three possible answers to the question, what order they happen in. According to one observer, they're simultaneous. According to a second possible observer in the same scene, it's B that happens first and then A. And then according to a third observer in the scene, it's A that happens first and then B. These three answers appear to be logically incompatible with each other. But what it shows you is that there's no actual objective ordering to the time sequence that you used to think was linear. Some events that you think are happening in the future and they're not real yet could be seen as having already happened in the past according to a different possible observer's vantage point. And that is very deep and weird because it starts to raise the issue. No, Brian, again, this is the misunderstanding I'm trying to ward you off from. In actual reality, there is no answer about them being simultaneous. It's not about the observer is the one getting things wrong. The events themselves are relative in the nature of things. If you had different measuring instruments, then they would not be able to agree because the transmission of light to anything that can observe happens in physical space according to the speed of light and the position and velocity of the object which can receive the light signal. So even if there were no observers at all, there would still be this mismatch between the ability to record or assign an order to the events happening. I'll send around some different videos, but this is not me just riffing off of it from my own personal point of view. This is the consensus view of science ever since Einstein wrote this work. So there's definitely no objective fact about the ordering of the events. Because again, look, the observer who is seen here, who appears to see them happening simultaneously, only sees that because relative to the other observer, he's motionless at end. But there's no particular reason to prefer his state of observation to the other person. A person could just as easily insist in the way that you are that the state of observation conducted from the position of the train is the correct one. There's no single observer's vantage point that serves as the leverage from which all others are to be judged. So we cannot say that he's standing in the correct position to observe the events and the other person is not. In fact, he's only motionless relative to a frame of reference that we've defined as standing on the embankment. In actual reality, he's not motionless at all because he's standing on the earth, which is moving at a high rate of speed. So there's no observer ever anywhere that is correctly stated as motionless when you take view of the bigger reference frame of the universe. So when we looked at the two lightning strikes, we just had a simple question at first. Are they simultaneous? And how could we define that? We defined a way of measuring simultaneity by placing an observer at an equidistant midpoint such that if they observe the two things happening at once and the speed of light is fixed, we could deduce that they departed from their origins at the same moment. But using that definition of simultaneity, we arrive at puzzling results. that there are multiple different ways that a person could observe the two events, either as simultaneous or happening in different sequence. Now that's what he says here. Before the advent of the theory of relativity, it had always been assumed in physics that the statement of time had an absolute meaning, that it was independent of the state of motion of the body of reference. So when you guys say there's got to be a real answer, you're thinking more in the realm of like Newton. He says, but we have just seen that this assumption is incompatible with the most natural analysis of simultaneity. If we discard this assumption, then the conflict between the law of the propagation of light and the principle of relativity disappears. Now, there's a little bit more weird stuff that follows from this too, that I would like to also kind of go over with you next time at the beginning. We also have to talk a little bit about the concept of time dilation and the twins paradox, which is fascinating. So there's a few more extensions of this. I want to talk to you guys about how, for example, the measurement of time can be different depending on how fast or slow you're moving relative to other observers. The basic principle, and I'll explain in more depth next meeting, is that if you're moving at a high rate of speed and another observer is comparatively at rest, then the way that you pass through time relative to that other observer is going to be slower than it is for the other observer. So if you, let's say, like in the movie, I don't know if you've ever seen it, what was it, Matthew McConaughey, Interstellar? In Interstellar, like if you had gone very fast, like in a rocket ship away from the Earth, and then you returned back to Earth, the fact that you had been moving at such greater velocities than all the terrestrial earthbound people would mean that when you returned, much more time would have passed for them than for you. So in one climactic scene from that movie, Matthew McConaughey has returned from all his interstellar space travel, and he's back on the surface of the Earth with his daughter, who now has become older than him, because time has passed so much slower for him than it has for her due to his much higher state of motion velocity-wise. So he's like comforting her on her deathbed because she's an older person than him. That's very strange, isn't it? But that's actually a proven consequence of this theory. Now, it's something that we don't experience on a macroscopic level because we cannot actually achieve such variable speeds as to make the difference in our experiences measurable or observational. But they do happen, and they've been measured in elementary particles that we're able to accelerate very fast in particle accelerators that we have got, that we've created. They can actually take a tiny little chunk of matter way close to the speed of light, and then you start to see their half-life dilate in time relative to others that have not been excited at that speed. You say you can't comprehend it, William, but that's not true. You can comprehend it because other people can, and you will be a person that will comprehend it as well, because I'm going to teach it to you. There's nothing about you or anybody else that makes these concepts impossible to understand. And actually, when you get a couple examples and a thorough explanation, you'll find that you're quite able and quite capable of understanding it. That's the thing about intellectual activity in the academy. You always have to believe in yourself that you can reach for a higher level of understanding. When you become intimidated by complex ideas and you say, this is too much, or I can't necessarily understand it, you're selling yourself a little short. I know you can do it. I believe that anybody can, especially the great capable group that we've got. So anyways, guys, I'm going to let you go for now, but I want you to have a great weekend and stay safe. In any case, I'll see you back on Monday, and we're going to continue reading our notes on time. So I want you guys to look at the writing of Ted Sider, and we're going to go over his paper on Monday, and I'll wrap up a few last things with this. So anyways, thanks so much, everybody. Take care, and I will definitely see you soon, okay? Bye.